Hi, in this example problem we are going to do an energy balance where we'll be equating the heat transfer rate by convection to that of conduction and using that to solve for an intermediate temperature. Let me just go ahead and read the problem statement. A plain wall that is 20 centimeters thick and has constant thermal conductivity of K equals 3 watts per meter per Kelvin undergoes one-dimensional steady conduction. The surface temperature on the left side of the wall is known, and the right side of the wall is exposed to air and convective heat transfer. What is the temperature at the interface between the wall and the air on the right-hand side, or T2? Okay, so obviously this is our wall. We have air on this side. We don't really know what's going on that side. So this is a plain wall, which implies that it's one-dimensional conduction, which means heat's going to be flowing in this direction. Well, heat's going to be flowing in the x direction either way. It's not going to be flowing in the z direction or in the y direction, which would be like in and out of the screen. So what we want to do here is find this interface temperature at the wall surface and the air, which is this T infinity equals 10 degrees Celsius. So it's important to kind of look at the problem and try to understand what's happening. Remember that the driving force for heat transfer is a temperature difference. So if we look at the two temperatures that we know, we would expect heat to be flowing from the high temperature to the lower temperature. And we don't exactly know what's happening here, but we expect that heat's flowing from here to here, and then it's flowing from here to here. So we would expect this T2 to be somewhere in between, because there's got to be a temperature difference from here to here in order for heat to get that far. And then there's got to be a temperature difference from here out into the bulk fluid in order for the heat to get into there. So that's sort of just conceptually what's happening in this problem. If we remember the different modes of heat transfer, remember that conduction happens through a solid. So we'd expect conduction to be happening in this zone. And then it's convection that happens from a solid surface out into a bulk fluid. So we'd expect conduction to be happening here, and then convection to be happening here. So we want to set up an energy balance that's going to give us some useful information. If you remember, you can set up an energy balance whenever, wherever, however you want, and you can be assured that energy will be conserved within that control volume or that control surface. However, that energy balance may not end up giving you useful information, so you have to be pragmatic and cautious about the way you're setting up your energy balance. So for us, we want to know this interface temperature. So at the end of the day, we want our energy balance to create an equation that we can use to solve for that intermediate temperature. So we want to be sure that however we set up our energy balance, that T2 shows up somewhere in it. So I'm going to recommend that we set up a surface energy balance, and I'm going to try and draw our control volume. We want the control volume to basically encapsulate this interface between the solid wall and the air. So I'm going to try to very carefully, I'm terrible at doing this, I'm going to try and very carefully draw my control surface here. And I apologize, that is not very straight, but that's the best I can do. I'm an engineer, not an artist. So this is basically our control surface. So we're going to assume that it has a width and a height, but it has no depth. So it's a two-dimensional shape. So it has no thickness to it and no volume. So let's keep that in mind. So we have our control surface, and if you remember, we want to write out our terms of the energy balance. So we have accumulation, we have in, out, and we have generation. So we just want to carefully think through how to quantify each of these terms. Let's start with accumulation. So first of all, we are told that this is a steady process. So if it's a steady process, our accumulation term, if we're doing the rate form of the equation, which we usually will, would be dE dt. So the fact that it's a steady process tells us that this is going to be 0. So we don't need an accumulation term, it'll just be 0. Another reason that we could justify the accumulation term being 0 is that we're dealing with a control surface and not a control volume. So our control surface, because it has no thickness and no volume, it has no ability to accumulate energy. There's no actual physical matter that can fit into this two-dimensional surface. So that would be another reason to that our accumulation term would be 0, whether it's steady or not. Okay, let's move on to our next term, the energy in term. So we made the assumption kind of by inspection and looking at our temperature driving forces that energy was going to be flowing this way. So if energy is flowing this way, energy is going to be coming in to our control surface by conduction. So how do we quantify conduction? This mode of heat transfer is associated with a rate equation, and that rate equation is given to us by Fourier's law. So we're going to put Fourier's law in here, and if you recall, Fourier's law tells us that heat transfer goes by minus k times dt dx. This is the flux version of it, and if it might be useful to deal with terms of energy rate. So instead of dealing with just flux, let's deal with the rate form, and let's multiply that by the cross-sectional area of our wall, which would be the height multiplied by the width. So the height in the z direction and the width in the y direction. We don't know anything about the actual dimensions of those, so we're just going to keep a in there as a placeholder. Okay, so energy is getting in to our wall, into that very interface. We'd want to measure what the derivative of our temperature with respect to x is right at that interface, or right at x equals L, with L being our wall thickness, which I have just now defined. Okay, so we want to measure our temperature derivative there. However, if you remember from a previous lecture and from your reading that for a plane wall of constant thermal conductivity and under a steady state process, that this temperature profile is going to be a straight line. So which means that the derivative dt dx is constant from x equals 0 all the way up to x equals L. So because this is constant, we can rewrite this form of Fourier's law to be the simpler form, and actually you can just take the rise over the run of your temperature and plug that in. So the dt dx would be equal to T2 minus T1 divided by L. So that's just the difference in temperature between here and here divided by the difference in our x, which is just L. So x equals L here at that right edge of the wall. All right, and now to put this in, to finish off Fourier's law, we would just have our minus k. So this represents dt dx, which just happens to be constant over the whole thickness of our wall, multiplied by our area. So if you notice, we already have T2 showing up as a term in one of our rate equations, so that's good. We are doing this correctly as far as we know so far. So I'm just going to take this term and clean this little equation up a little bit, and I'm going to substitute this in here. So here we've got minus k times T2 minus T1 over L, and we have that multiplied by A. So this is an in term, so this is the absolute value of our in term, and it's even though it's an in term, it does have a negative on there, so don't panic or freak out. That's the form of Fourier's law. It always has that minus sign unless you do some algebra and rearrange this. So as an in term, you always want the conduction to have that minus k on it, but you want to think very carefully about how you're defining your temperature difference. All right, let's think about now our out term. How is energy getting out of our control surface? So it's coming from this surface and it's leaving across the boundary. How is it leaving? Well, that is by convection. So our out term is going to happen from that surface at the interface out to the right into this air by convection. So our out term is going to be by Newton's law of cooling, which is HA times T2 minus T infinity. So this is how, so we've applied Fourier's law here. And Newton's law here. To get conduction and convection respectively. All right, what about generation? So we're not told anything about generation in this problem, so we can assume it's 0, but also generation is typically happens on a per unit volume basis, or at least that's the way it's characterized in this textbook. So our control surface has no volume. If you remember, it has no thickness, so it has no capacity to generate. So that term is going to be 0. So if you remember to compile our energy balance, we take accumulation is equal to in minus out plus generation. So we have 0 for our accumulation term is equal to minus k times T1 minus T2 times A divided by L, subtract H A times T2 minus T infinity, and that's our equation. So now we have one equation and we have one unknown because each of these other quantities, K is known, T1 is known, L is known. A, actually, I misspoke. A is not known, but however, you can see that if we were to rearrange this equation, we can actually just take A out of there. Or we could just assume that the wall is 1 meter by 1 meter and plug that in as a basis, but I'll just choose to delete it. So we know H and we know T infinity. So we have one equation, which we derived because we are starting to learn about how to characterize rates of heat transfer by these different rate equations. We used this energy balance to generate this equation. We have one equation and one unknown, and now we can go ahead and solve the algebra of this system. So I'm going to, you can certainly do this on your own, and I would encourage you to do that, especially if things aren't seeming like they make sense to you. I'm going to go ahead and skip a lot of the algebra and just write in our final equation after solving for T2. So we get that T2 is equal to K over L times T1 plus H times T infinity divided by K over L plus H. And this is just algebra from taking our energy balance and rearranging to solve for T2. As I've mentioned several times, it's really important to do a unit check. So far we've gotten to this point without even thinking about units, and that's actually the way I would encourage you to do it. Get really good at quantifying the different rates of heat transfer and understanding the concepts, and then use unit analysis only to check your work. So unit analysis is a great tool to check your work. So we're going to be adding this term and this term together, so we want to make sure that they have the same unit. So let's look at the first term. K has units of watts per meter per Kelvin. It's also divided by L, which has units of meters. We then multiply this term by T1, which has units of degrees C, but since everything we're doing is on a delta T basis, we can just call that Kelvin for now. We could also think about each of those in terms of degrees Celsius. We don't really have to worry about absolute temperatures much unless we're dealing with radiation, where you're doing things like taking temperature and raising it to the 4th power. There may be other instances where you need to work in absolute temperatures. Okay, so then let's look at this other term. So H, it has watts per meter squared per Kelvin, and T infinity has Kelvin or degrees C, but we're going to use them interchangeably for now. Okay, so here we get the K's cancel out, and each of those terms has units of watts per square meter. Okay, let's look at the denominator here. So K has watts per meter per Kelvin, L again is meters, and then H is watts per meter squared per Kelvin. Okay, so on the denominator we get watts per meter squared per Kelvin. Where any terms that are additive, we want to make sure that they have the same units, or you shouldn't be able to add them together. So these two terms on top would both add together, these two terms on bottom would both add together, and we end up with units in our numerator of watts per meter squared, and in our denominator we have watts per meter squared per Kelvin, which is equivalent to just Kelvin. So that's great. And we could also think of this as degrees C. And actually, once we plug and chug everything into here, we end up with a temperature of T is equal to 18 degrees C. So that is our final temperature. Let's go back and make sure that this temperature makes sense. Let's just do some inspection. If you remember when we were talking about our temperature difference as a driving force, we surmised that we would expect T2 to be somewhere in between T1 and T infinity, and that is in fact true. So T2 is 18 degrees C, so that's good proof and a good check of our work. So we know that heat is going to still have that driving force by conduction, with this 50 gradually decreasing to 18 as the driving force in our solid wall, and then 18 to 10 as the driving force for convection. That's it for this problem. Thank you very much.